I welcome all of you to the class on planar kinetics of rigid bodies. As far as the kinetics of rigid bodies is concerned, in the kinetics of rigid bodies, we do talk about the analysis of the rigid body motion, taking into consideration the forces that act on the rigid body. Now, before we go ahead in understanding the kinetics of a rigid body, so kinetics is all about understanding the motion of a body. Okay, so in kinetics we obtain what we call as the equations of motion. Okay, using the kinetic principles we obtain the equations of motion that define the motion of a body. The question is like, let me suppose that we have a rigid body. Let's suppose we have a rigid body, and this rigid body is, say for example, lying on a flat surface. Okay, we have, say for example, a flat surface. We have a rigid body, and this rigid body is lying, say for example, on a flat surface. Now, as far as the rigid body is concerned, let's suppose that this rigid body happens to move in some direction on this plane surface. Now, as far as the rigid body is concerned, a rigid body is composed of an infinite number of points. Okay, it's composed of a collection of infinite number of points. And if we take this point, let's consider this point of the rigid body as point P. Okay, we assume this to be the point P. Let's suppose this is a point P. This is the rigid body, and this rigid body is, say for example, it's acted upon by some forces. A number of forces are acting on this rigid body. Okay, let's suppose force F is acting on this rigid body, and this rigid body is, say for example, let's suppose because of the application of forces, let's suppose this rigid body is accelerating. Its acceleration is A. Okay, let's suppose its acceleration is A. Now what we do, we have selected a point, what we call as a point P. Okay, we select a point and we call that point as the point P. Now, as far as this point P is concerned, first of all, as far as the force F is concerned, we have to understand the application of the force F on the rigid body in causing the acceleration, and some other parameters which are created by the force F while it creates motion in a rigid body. What I mean to say is, first of all, look at a collection of a number of, this rigid body is composed of a number of points, number of particles, and these particles are very, very close to each other. So this rigid body, we say it is composed of densely packed collection of particles. So particles are very, very close to each other, and we say this is a collection of densely packed, these are densely packed particles. Okay, now what we do, let's take a small element of this rigid body. Let's take a very small element of this rigid body. Okay, and let's suppose the total mass of this rigid body is m. The total mass of this rigid body is m, and let's suppose the mass of this small element is, say, is very, very small. Let's call this as dm. Dm is the small mass of this small element that we have selected. Now, the small element that we have selected, it has a small mass, and we call this mass as dm. Now, in small mass dm, and let's suppose from point P, this small area element, let's suppose it lies at a distance, and let's call that distance as, let's say it lies at a distance r. It lies at a distance r. R is a vector. It lies at a distance r from point P. Okay, then what we say, we define for this rigid body, we define a particle what we call as the center of mass. We define a particle called as the center of mass. The definition of, the mathematical definition of center of mass is, the definition of center of mass is equal to integral of a radius vector to the mass element dm, that is integral rdm, integral of rdm divided by integral of this mass element, that is dm, and we call this as this is the position of the center of mass. That likewise, as you have been given in as the centroid, you said the x bar, x coordinate of the centroid is integral of x dA divided by integral dA. Okay, this is how we define the centroid, and we define the y coordinate of a centroid of a rigid body as y bar is equal to integral of y dA divided by integral of dA. Okay, with these definitions, these are the definitions of what? These are the definitions of the x and y coordinates of a centroid of a plane area. Now, when you are considering the mass of a body, while considering the mass of the body, we take the coordinates of the center of mass, and we define the center of mass is given by this definition, integral rdm divided by integral dm, and we write this as, this is the position of the centroid as measured from point P. We write this as r p c, that is position of the centroid as measured from point P. Okay, this is what we call as, this is how we define the center of mass of a rigid body. And center of mass of a rigid body, by some simple definitions, it is a point where the entire mass of the rigid body is supposed to be concentrated. Now look at the rigid body. As far as the small element that we have selected, we said its mass is dm, and this mass dm will have the same acceleration as the acceleration of this rigid body, and let's suppose its acceleration is a dm. Okay, therefore, as far as this rigid body is concerned, as far as this small mass is concerned, small area element is concerned, this small element is subjected to force, and that will be equal, this small element dm is accelerating, it is accelerating with an acceleration of a. Okay, as the acceleration of rigid body is a, and we know from Newton's law, force is the product of mass and acceleration. Therefore, the force acting on this small area element will be equal to its mass, that is small mass dm, multiplied by the acceleration, that is a vector. So that force will be in the direction of the acceleration. Let's suppose that small force is df vector, and this df vector acts in this direction. So for the small area element, for the small mass element, the force acting is df. Now look at this df. This df is having some radius vector from point P. Okay, and from the definition of the torque, there will be some moment of this force, small force df, about point P. Therefore, we can write the moment, the small moment dm, the small moment about point P, because of small force df, will be equal to the radius vector, that is r, cross the force, that is r cross df. Okay, this is the small moment created by the small force acting on the small mass element dm. Okay, therefore, the total moment because of this force about an axis passing through point P will be equal to integration of this equation, that is integral dmp will be equal moment about point P is equal to integral of r cross df, and as far as df is concerned, df is equal dm into a, dma. Okay, so that can be written as a into dm. Okay, therefore this term can be written as, therefore this can still be written as, we can write this expression as, we can write this as moment of force about point P is equal to, moment of force about point P can be written as integral of, this is r, so we can write this as r multiplied by dm, r dm multiplied by r, sorry, this is not multiplied, this is cross product with acceleration a, cross product with, not multiplied, this is cross product with acceleration a. Okay, now as far as this acceleration is concerned, this is not only the acceleration of the small particle, this is the acceleration of the entire rigid body. Okay, so this can be written as integral r dm cross product with the acceleration. And if you look at this rdm, this rdm from the definition of center of mass can be written as integral dm is equal to m And as far as this RPC is concerned, this is the position vector drawn from point P to the centroid. Therefore, this RDM, integral RDM can be written as, this can be written as RPC. This is RPC, this is RPC, and you have integral dm, that is equal to m. That m we can multiply with a, that's equal to m into a. Okay, this is equal to, this is equal to the resultant moment about point P. Okay, so remember this equation. Okay, this equation is a very important equation that we must remember. Two things are there. When a rigid body is undergoing motion, the motion of a rigid body, if you recall, while we were dealing with the kinematics of rigid bodies, we were taking the example of the duster. Okay, so we had a duster. So as far as the duster was concerned, the motion, if we were trying to visualize the motion of the duster, okay, so sometimes this duster, as the duster is given motion, it will have, it will attain many configurations. Okay, while a teacher is rubbing the board, so the duster attains a number of configurations. Okay, so if you look here, this is the configuration 1, but if you look here, this is configuration 2, and you know configuration 2 is obtained by translating configuration 1 as well as rotating configuration 1. Okay, that is, if you first of all, if you rotate this configuration 1, if we rotate this configuration 1 in this way, okay, if we rotate this configuration 1 like this, and then we translate this configuration, rotated configuration, to this position, we will obtain position 2. That is, position 2 is obtained by rotating configuration 1 as well as translating configuration 1. So as far as the planar motion is concerned, in a planar motion is the combination of two motions. In planar motion, we have the combination of two motions. First one is we have translation. Okay, we have translation, and second one is we have rotation. Okay, second one is the rotational motion. So that's why we are dealing with, whenever we are talking about the motion, planar motion, we are using translational equations of motion as well as rotational motions of equation, like we are taking this equation into consideration. Okay, so when we talk about the planar motion of the rigid bodies, okay, like if I if as I was giving you an example here, okay, like I gave you an example right now, like you have a duster here. Okay, this duster is being used to rub the board. Now after some time, as the teacher rubs the board, the configuration of the duster will be, say for example, like this. Okay, so if you look at this configuration, we call this as configuration 1, we call this as configuration 2. If you look at configuration 1 and configuration 2, the difference between configuration 1 and configuration 2 is configuration 1 has been obtained by first rotating this configuration 1 about its axis. If you rotate it about its own axis, okay, you will obtain the same picture as configuration 2. Okay, then once this element has been rotated, once we rotated this element, once we rotated configuration 1, and then we translated this configuration 1 to this position. Okay, so first we rotated it, then we translated it. So planar motion is associated with two motions. One motion is the translational motion, second one is the rotational motion. As far as the translational motion is concerned, always remember the resultant of all the forces by Newton's second law of motion, the resultant of all the forces acting on the rigid body is equal to the product of mass of a rigid body and the acceleration of center of mass of the rigid body. Okay, this is a very important equation. F is written as m into ac. This is what we call as the translational equation of motion. That is, force acting on a rigid body is equal to the product of mass and acceleration of its center of mass. And as far as the rotational motion is concerned, that is given by the equation summation of all the moments about point P. Summation of all the moments about point P is given by the equation RPC. RPC is the radius vector drawn from that point to the center of mass, cross product with the acceleration of the rigid body or the acceleration of the center of mass. Let's see how we can use these two equations in solving the problems of kinetics. Let me take a problem from your book. For example, we have a very simple problem. Before we have a solved problem out here. Before I solve this solved problem for you, let me go to an unsolved section to show you how we make use of these two equations. Let me take a very easy problem. Let me take this problem of a cart. As far as the problem is concerned, the problem says the cart and its load have a total mass of 100 kg. So we are having a cart, okay? This cart is having a total mass of 100 kg along with the load that is inside it. Determine the acceleration of the cart. We have to find the acceleration of the cart and the normal reactions on the pair of wheels at A and B. Neglect the mass of the wheels. So what the question says, as far as the question is concerned, some force is being applied on the cart, okay? As the force of 100 Newton is applied at some angle, that is causing, so force of 100 Newton is being applied on the cart, because of which there is translational motion, because of which the cart is translating in the forward direction. So we say a force of, so force of this much of force of 100 Newton is acting in this direction in such a way, that it's, as is given here, as far as the base is concerned, the base is its base is 3 units. As far as the what you call as the perpendicular is, that's given as 4 units, okay? And the force that's acting on the rigid body is, the force that's acting is equal to the force of 100 Newton is acting in this direction. And this force of 100 Newton is causing the motion in the rigid, in this cart, and this cart is translating forward in this direction. We have to find the acceleration. What is the acceleration with which it's moving forward? Number one. Number two that we have to find. See, as far as the cart is concerned, apart from this force of 100 Newton, there is also the gravitational weight of the cart, and the gravitational weight of the cart will be acting in the downward direction. Now, this 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 gravitational weight will be creating, will tend to move the cart in the downward direction, but the cart's wheels is having contact with the surface, as a result of which at the surface, at this surface, at the point of contact between the wheel and the surface, a normal reaction is generated in the upward direction. So we'll be having normal reaction at point A, and we'll be having normal reaction at point A. We'll be having normal reaction at point A, and we'll be having normal reaction at at and A and B. The reason for this normal reaction is, see, the gravitational weight of 100 kg, that is mass, into 9.81 Newton is doing what? Is trying to move the cart in the downward direction. But if the cart does not have to go in the downward direction, therefore at the point of contact between the wheels and the surface, a normal reaction has to be produced in the upward direction that nullifies the effect of the effect of the gravitational weight. So we write a reaction at end B. Let's write that as RB, and the reaction at end A, let's write that as RA. Okay. So what we have to do, we have to analyze the motion of the body to find the acceleration and to find the value of RA and RB. So what we do, first of all, let's write the equations of motion. As far as the equation of motion concerned are, we have summation of all the forces, the equations of motion that we have in hand. Summation of all the forces acting on the rigid body is equal to the product of mass and acceleration of a rigid body, okay? And number two equation that we have is summation of all the moments about any point P is equal to the radius vector drawn from point P to the center of mass, its cross product with the mass and acceleration of the rigid body. We'll use these two equations to solve this problem. First of all, sum up all the forces. See what type of forces are acting on the body. Summing up all the forces along x-axis, that becomes equal to, okay? So do you have a gravitational weight along x-axis? No. Do we have RA and RB along x-axis? No. So let's treat this to be our x-axis. Let's say this is our x-axis, and let's treat this to be our y-axis, okay? So this we treat as our y-axis, and we treat this to be our x-axis, okay? So RA, RB, and this gravitational weight are not along x-axis, therefore they do not have anything along x-axis. So what we have along x-axis, we are having a force of how much? We're having a force of 100 Newton, which can be resolved into two components, okay? So we have a force of 100 Newton, which can be resolved into two components. Its one component will be in this direction, and its another component will be in this direction, okay? And as far as the component in this direction is concerned, if we take this to be our theta, the component in this direction will be 100 cos of theta, that is base by hypotenuse, okay? If we take this to be, that is base by hypotenuse, that is 3 by 4. Oh, sorry, 3 by 5. Okay, so that is 3 by 5 in this right angle triangle. Cos 100, cos 45, sorry, this is the theta. Cos 45 will be base by hypotenuse, that will be 4 by 5. So this is, we have to take this as 4 by 5. This is its one component. Okay, and this component, this component of the force, this component of the force, this is one of its component. Okay, now another component will be, or if I make draw the angles properly, I'm not drawing them here properly. So if you look here, this angle is given to us as, in this right angle triangle, if this force of 100 Newton is acting in this direction, now it is moving in such a way that with respect to the base, it is subtending some angle. Okay, therefore its component in this direction will be the component of this force in this direction we have to find, and in this direction we have find. As far as this component is concerned, this angle and this angle will be vertically opposite, so this will be the component in this direction will be 100 cos of theta, that is 4 by 5, 104 by 5, and the component in this direction will be 100 sine 45, that is 3 by 5, that is 100 sine 45 is equal to 3 by 5. Okay, so summing up all the forces along x-axis, we are having 104 by 5 Newton acting along positive x-axis. We'll take that as positive. That is 100 into 4 by 5 force Newton. There is no other force acting along x-axis except this force. That has to be equaled by this equation. Mass of this body, that is 100 kg, multiplied by the acceleration of the body. 100 and 100 cancels. Therefore, acceleration becomes 0.8. So acceleration of this body becomes 0.8 meter per second square. So we are done. We have to find the acceleration. We are done with the acceleration. Now we have to find the normal reaction at end B, at and at end A. So what we write, let's write summation of all the equations along y-axis. When we write summing up all the force equation along x-axis, y-axis, we have RB acting along positive y-axis. We write this as RB. RA is also acting positive y-axis. We write RA plus RB. Okay, so RA is acting positive y-axis. RA is also acting along positive y-axis. We wrote them RA plus RB. We are having gravitational weight acting in downward direction, that is minus 100 into 9.81, that is 98.1. We are having a force of 100 into 3 by 5, that's equal to 60 Newton acting again downwards, that will be minus 60 Newton. No other force is acting along y-axis, therefore this has to be equal product of mass multiplied by acceleration along y-axis. The cart is neither going up nor going down. It does not have motion along y-axis, therefore its acceleration along y-axis will be 0. That is, the entire equation will be equal to 0. Therefore we can write, as far as RA plus RB is equal, RA plus RB becomes equal to 98.1 plus 98.1 plus 60 becomes equal to 158.1 Newton. Okay, so as far as RA plus RB is concerned, RA plus RB becomes equal to 158.1 Newton. Okay, this is fine. Now let's start taking the moments in order to find the value of RA and RB. Let's take the moment of all these forces about point B or about point A. So what I mean is, let me rub it. Let's rub this term. Oh, sorry. Now we have to find the normal reaction. In order to find the normal reaction, let me rub these equations. We have the equations in hand. Let me rub these as well. Okay, fine. Now let me go back to the, so I used the equation summation is equal to the force of product of mass and acceleration, that is fine. Now let's use the second equation. Okay, so second equation is the second equation is moment of force, summation of all the moments about point P is equal to the cross product RPC cross mass times the acceleration. Okay, if you look at this RPC, this is the point P. For example, if you take this has to be point P. Okay, from point, if you have to calculate all the moments about point P, okay, then what you have to do, the PC will be the vector drawn from this point to the center of gravity, that is given to us here as G. Okay, that's one. But if you take the moments, if you don't take the moments about point P, if you don't take the moments about point P, if we take the moments about the center of gravity, okay, therefore what happens to the radius of center of gravity, what happens to the radius vector drawn from P to center of gravity, that is if we move this point P to center of gravity, if you look at this radius vector becomes equal to 0. So as this radius vector becomes equal to 0, therefore I mean to say, if I don't take the moments about point P, but I take the moments about the center of gravity, therefore moments about the center of gravity become equal to the radius vector from the center of gravity when we had the moments about point P. Okay, so it was RPC, the radius vector drawn from point P to point C. If you have to take the moment about point G, center of gravity, then it will be RPG, radius vector drawn from the center of gravity to the center of gravity. That will be equal 0. So 0 cross MA becomes equal to 0. This is a very important result. It means the moment of a rigid body, the summation of all the moments of a rigid body in its planar motion, particularly when the body is translating, for a translation case, for a rigid body, the summation of all the moments about the center of gravity is equal 0. This equation we will use to find the values of RA and RB. So how we find the value of RA and RB? This is very easy for you. You can clearly do it. This is RB. This is your RA. What forces you have acting in the along y direction? The forces that are acting in the y direction. So you had one of the force acting along y direction like this. Another force was acting along x-axis. Okay. So what we will do, we'll write the equation. So this is our RA. Sorry, this is RB. This is RA. Okay. So we'll write now. We'll use this equation. Taking the moments about the center of gravity. Imagine the axis is passing through the center of gravity. Take the moments about center of gravity. The first moment will be because of RA. That is, moments about the center of gravity will be equal to the radius vector from center of gravity to the line of action of the force, that is 0.6 meter, multiplied by the value of the force, that is RA. 0.6 into RA. What is this RA trying to do? If you look here, this RA, if we apply a force in this direction, it will lift the cart in the anti-clockwise direction. You take anti-clockwise moments as positive. Okay. Then we have RB. The moment because of RB will be RB multiplied by force arm, that is 0.4. But it's trying to rotate the cart in the clockwise direction. We'll take this as minus. So it is minus 0.4 minus 0.4 RB. Okay. And then we'll be having the moment because of this force. This is also trying to lift the cart. If you apply the force on the handle in the downward direction, the cart will rotate in the anti-clockwise direction. Therefore its moment is to be taken as positive, and its magnitude was equal to 60 Newton, I think. So its magnitude was 60 Newton. Its magnitude was 60 Newton. So this is 60 multiplied by the force arm, that is 0.4 plus 0.3, that is 0.7 meter. Okay. And this force that was acting in this direction, that was equal 4 by 5 of 100, that was 80 Newton. This force, the moment of this force about center of gravity will be 80 multiplied by the distance from center of gravity to this very point. Okay. The moment of the center of gravity to this point is 0, and it's trying to rotate the cart in clockwise direction. It is minus multiplied by, this is at the geometrical center. Sorry, the distance from here to here is 0.5. This total distance is 1.2. Therefore, the distance from here to here will be 1.2 minus 0.5. That's equal to 0.7. Okay. This is the summation of all the moments about center of gravity. This entire has to be equal 0 by this equation. Therefore, we can write 0.6 RA. We can directly write here. We have 0.6 RA, 0.6 RA minus 0.4 RB minus 0.4 RB. This entire thing is 60 into 0.7 minus 80 into 0.7. That becomes equal to 60. That becomes equal to 20 into 0.7 that is equal to 14. So that will be, this is equal to 14. Okay, so now we have two equations. We have equation, I will write this as equation 2, and I have equation 1. Ra plus Rb is equal to 158.1. 0.6 Ra minus Rb is equal to 14. From these two equations, I can obtain the value of Ra and Rb. So what I will do, I will multiply equation 1 by 0.6. If you multiply equation 1 by 0.6, multiply this by 0.6, so it will be 158.1 multiplied by 0.6, that becomes 94. That becomes 94. That becomes 94 point, that becomes 94.86. Okay, so now I will add up this equation and this equation. So as I add this equation, so, or if you I will subtract this equation from this equation. So 0.6a, 0.6a will cancel. This is 0.6 Rb plus 0.4 Rb, that will be equal, Rb becomes equal to 94.86 minus 14, that is equal to 80 0.86 Newton. Okay, therefore the value of reaction at B, how much is the value of reaction at B? The value of reaction at B is equal to 80.86. So I know Ra plus Rb is equal to 158. From this equation I know the value of Rb, therefore we can calculate the value of Ra. The value of Ra will become equal minus 158.1, that becomes equal to, the Ra value becomes equal to, the value of Ra becomes equal to 77.24 Newton. Okay, so by using two equations, we could understand the reactions Ra and Rb as well as the acceleration of this car. Okay, so this is how we have to solve the problems on kinetics of rigid body using the equations of motion. I will again consolidate on these concepts, helping you in solving the problems to make you more understand the equations of force and acceleration in analyzing the motion of the rigid bodies in the coming up classes. Thank you very much.